Chapter 6 of the Abstract Algebra series is on relations and functions. Number 1 wants to know what would be the cross product or the Cartesian product of sets A and B if A contains the elements 1, 2, and 3, and B contains the elements 3 and 4. So again, we're looking at the Cartesian product of sets A and B, and this product produces the set of all possible ordered pairs x, y, where x is an element in A and y is an element in B. Since A has 3 elements, and those 3 elements may each be paired with one of the 2 elements in B, there are 6 ordered pairs in the Cartesian product. And those would be 1, 3, 1, 4, 2, 3, 2, 4, 3, 3, and 3, 4. Notice again, these are ordered pairs where the first number in each pair has to come from set A, the second number in each pair has to come from set B. And if you look down at the graph here, we have a picture of the cross product here, or the Cartesian product. And let's see, this point here would represent the point, first of all, let's look at what we might call the x-axis. We'll say that this is the set A, which contains elements 1, 2, and 3. And over here we have set B, which contains elements 3 and 4. So this dot here in the upper left, that's going to be 1, 3. The one directly beneath would be 1, 4, and then moving on over to the second column, I would have 2, 3, 2, 4, and then 3, 3, and 3, 4. So this is just a pictorial representation of the Cartesian product between these two sets. So imagine if sets A and B contained all of the real numbers, and we took the Cartesian product of all real numbers in those sets, we would actually generate the entire XY plane, the one that we're so familiar with from our algebra courses. Notice that this relation is not a function because each element in A is mapped to 2 elements in B. In other words, these points here would fail the vertical line test. And that happens because 1 is mapped to 2 values, 3 and 4, and then 2 is mapped to 2 values, 3 and 4, and so on. So even though this is a relation, this relation is not a function. Okay, number 2. Number 2 says, show informally that the set of all rational numbers is countably infinite. And in most mathematics courses, this double-edged Q here represents the set of all rational numbers. And we want to show that that set would be countably infinite. Well, Q would be countably infinite if there is a bijection from Z to Q. And the bijection actually should be from Z plus to Q, because we want to send all of our counting numbers, 1, 2, 3, and so forth, we want to map all of those to the set of rational numbers, as if we were actually labeling each number in the set Q, as if we wanted to count them. So how do we do that? The trick is to make sure that the first element in the set is 0. And we represent that with 0 over 1. And then we move over and we keep the denominator of 1. And we use 1 over 1, and then we alternate and use negative 1 over 1. And then we switch the denominator to 2, using 1 over 2, and then negative 1 over 2. And again, these rational numbers are fractions, they're proper fractions, which means that the numerator is going to be less than the denominator. That's the typical fashion when dealing with rational numbers. Of course, the denominators cannot be 0. And I use these ellipsis points here to indicate that this numbering pattern would continue. In other words, the next one in the list would be 1/3, and then -1/3, and then we would do 1/4, and so on. Eventually, we would run out, we would exhaust using 1 in the denominator and 2 in the denominator, and we would switch to any number b, right? We would switch to denominator b, and we would continue to alternate the numerators. So here, sort of in between, I'm just letting you realize that all we have in this list are a series of alternating fractions, in the sense that they're just positive and negative images of each other, so to speak. And somewhere down the line, we would probably have 100/313, and then -100/313. And of course, this list goes forever, right? We would just continue to alternate through all of the possible fractions in Q. But what happens if you randomly choose any element in Q? In other words, let's say that we press the stop button here, and we take a look at this particular rational number. Isn't it true that there is a finite number of elements, right? There's a finite number of rational numbers in the list, because this list started with 0. And this would be, say, the first element, right? 0/1 would be the first element, 1/1 would be the second element, and then we have negative 1/1 for the third element, then we switch to 1/2, -1/2, and we're just numbering these. At some point, I would be able to assign a number to 100/313 because it has a finite number of elements in front of it. Granted, it is probably a huge number, whatever that is. But the point is that we can label each of these rational numbers using positive integers, because we're looking to assign a unique positive integer to every element in Q. Since we're able to do that, then that means Q is countably infinite. In other words, we can assign a numbering system to keep track of how many we have. So they are countable, and they are infinite, of course, because this numbering pattern would continue indefinitely. Number 3. Problem number 3 is asking us to determine the inverse of a function. You probably remember how to do this from your Algebra 2 classes. But just in case, let's take a fresh look. We're being asked to determine the inverse of a cubic. In this case, it happens to be x cubed plus 5. So how do we find the inverse of a function? The standard is as follows. Typically, we start off by writing the function, and we substitute in y for f of x. So that would be y is equal to x cubed plus 5. So the first step is we rewrite the original, and if the problem is not using y in place of f of x, then that's typically our first move. We will call f of x y. That gives us y is equal to x cubed plus 5. That's the first step. Get everything in terms of x and y. The second step, interchange x and y. In other words, y becomes x becomes y. So our new equation is x is equal to y cubed plus 5. Now we solve for y using algebra, so I subtracted 5 from both sides in this step, giving me x minus 5 is equal to y cubed. And then to solve for y, the new y, I just take the cube root of both sides. So the cube root of x minus 5 is equal to y. But remember, this y is the result of that temporary switch that took place in step number 2. Remember, we swapped x and y here. Since this is really just a placeholder to make the algebra more simple, we're going to change this y to what it really is, f inverse. This y is f inverse. It's the inverse function. So what does that mean? That means that f of x, let's see if I can write this out here. F of x is the original problem, x cubed plus 5. And then we figured out that the inverse function, f inverse of x, is equal to the cube root of x minus 5. So what do we do from here? Well, if we graph both of these functions, look at the pattern that emerges. The cubic, the original, is graphed in red. And notice that it passes through the point 0, 5. And the inverse function is graphed in blue, and it passes through 5, 0. And 0, 5 and 5, 0 appear to be switching domain and range values. But that's typical. That's always what happens with inverse functions. The domain of one is the range of the other and vice versa. In this instance, they actually share a point. The x and y values are both negative 1.904. That's an approximation. But the key thing to notice about functions and their inverses, since the domains and range are interchangeable, so to speak, the graphs will always reflect into each other through a line, through the line y is equal to x. So if you could imagine a line that passes through this point, the origin, and keeps going. This is a terrible sketch, but I hope you get the idea. Imagine that this line here, y is equal to x, imagine that as a mirror. And as you can see, 0, 5 would pair up with 5, 0 on the other side. In fact, any point that you find in f of x will have a mirror image point on the other side for f inverse of x. Again, anytime you graph a function and its inverse, they will always be reflections of one another through the line y is equal to x. Number 4. Number 4, we have two functions that are actually permutations on the set of 3 elements. The 3 elements are 1, 2, and 3. Notice that f, the element 1 maps to 1, 2 maps to 3, and 3 maps to 2. And then if you look at element g, 1 maps to 2, 2 maps to 3, and 3 maps to 1. And we're asked to specify f of g and f of f. And I'm going to make an assumption here that should be relatively safe if you're taking abstract algebra. You do have quite a bit of experience with composite functions. And that's exactly what we're going to do here. F of g is a composite function, and f of f is a composite function. And we go from right to left. So let's go ahead and take a look at the first problem. We're asked to evaluate f of g. Well, f of g requires us to start with the permutation g because g is on the right side. And we will map its domain values on the top row to its codomain values on the bottom row. In other words, if we go back to g, we can see that 1 goes to 2. We can see that 2 goes to 3. And then 3 goes to 1. So this is going to be our beginning, right? These are going to be, g is going to take our first domain values and map those, and then we're going to slide over to the left and evaluate according to the element f. And again, g takes 1 to 2. We know that g takes 1 to 2. And once g takes 1 to 2, notice that f takes 2 to 3. So if 1 maps to 2 under g, and then 2 maps to 3 under f, then the overall composite function takes 1 to 3. And that's represented here in this column. Now let's move over in element g, and let's see what happens with 2. Well, at first, 2 maps to 3. That's under g. But then 3 is mapped to 2 under f. Again, 2 maps to 3 in g. 3 maps to 2 in f. So the overall composite function f of g takes 2 back to 2. And likewise, 3 maps to 1 in g. And then f takes 1 to 1, so in this case, 3 maps to 1. And again, this is the way we would write it in table notation. That would be our final answer. So let's talk about f of f without as much detail. F of f means that we're going to pick up in f, we're going to map it to f and see what the outcome value would be. Let's start with 1. Well, f maps 1 to 1, and then mapping again through f, that 1 goes back to 1. So 1 goes to 1. In f, 2 goes to 3, but then if you go back through f again, the 3 would map to 2. In other words, 2 maps to 2. And then f maps 3 to 2, and if you do the operation again under f, then you have 2 going to 3. So that takes 3 to 3. And by the way, this would be our identity function, right? The identity function maps any element back to itself. And problem number 5. In problem number 5, we have 2 functions. F of x is equal to x plus 1. This is just a line of slope 1, intercept 1. And then we have g of x, x minus 1. Same slope, slope of 1, different intercept. Intercept value here would be negative 1. And we are going to take a look at g of g in standard function notation. In this case, in the prior problem, we used table notation. Now we're just going to use standard function notation. So what does g of g look like? Well, g of g is the same thing as g of x, which can be written this way. And since g of x is equal to x minus 1, I'm going to substitute in x minus 1 in place of this g of x. Makes it a little clearer now that the domain is x minus 1, which means I go back into g. And in place of the x, I'm going to plug in x minus 1. That's the domain value. Well, if I plug in x minus 1 in place of x, that's going to give me x minus 1 minus 1, which is x minus 2. Let's take a look at f of f. Well, f of x may be written this way. And again, I'm going to substitute in for, in this case, f of x for the domain, which means x plus 1 is my input value. At this point, I go back to the function f of x, and I'm going to substitute in for this x plus 1. Once I do that, I have x plus 1, which simplifies to x plus 2.